In the third part, I will talk about how to write your own solution to the problem and how to submit the result. Before talking about how to write program, I will talk about different tracks of the computation. As the task is a complex one, there are totally 3 tracks in this computation. In the main track, you can modify both the perception module and planning module. You can also design your own structure instead of the perception and planning one. In the perception track, you only need to modify the perception module. Your own perception module and the planning module of baseline solution will be used at last. And in the planning track, you only need to modify the planning module. However, if you participate in the perception track or planning track, the score will also appear on the main track, and only top participants in the main track will be awarded. For example, Team T1 takes part in the perception track and gets an error of 0.052, which the lower is better, and it will be introduced later. So it has both the score on the main track and on the perception track. T2 takes part in the main track, and T3 takes part in the planning track. T4 also takes part in the perception track. As we can see that T1 gets the best score and will be the winner. The most simple way to participate in the perception track is to substitute modules in baseline solution. In the solution, the perception result is given by a row service whose format is defined in OCRTOC message. This service returns a list of perception result message, which is also defined in OCRTOC message. This message is composed of 2 parts, namely the object pose and graph pose. When you modify the perception module, you have to generate the message with the same format. As mentioned above, you can also substitute some of the functions in the perception module. GraphNet is responsible for generating graph poses, and postcorrespondence.py and post6d.py are responsible for estimating object poses. You can use your own code to replace them. For planning, the steps are similar, but there are only 2 important files, namely motionplanning.py and taskplanning.py. You can write your own program with the same interface. There are also some other options. You can modify both parts of baseline solution. And if you don't want to use the perception and planning structure, you can use your own structure, but you need to modify the rows launch file as shown here. On top of that, I will talk about the interfaces. For ROS users, there are a lot of available ROS topics that you can retrieve from or send to, so that you can interact with the hardware or the simulator. 4 types of ROS topics are guaranteed to be the same in both real robot branch and simulation branch. They provide interfaces for reading camera information, retrieving transformation, controlling robot, and controlling the gripper. The detailed topic names are shown here. For TF, only the transformation between these 13 frames are guaranteed to be valid. You can control the gripper and robot through the second and third topic respectively. You can also access camera information via these 8 topics, and you can read the joint angles via the last topic. There are many other topics in simulators or the real robot, but the consistency is not guaranteed and thus not suggested to use. Here are some examples for using ROS interfaces. First, you should bring up the backend. Move it should also be launched through the command. Then we will see that RViz is open. RViz, which means ROS Visualizer, is a powerful tool in ROS. You can do a lot of visualization using RViz. First, you can visualize TF or transformations among frames by adding a TF module in RViz. The result is clearly shown. Then you can also draw the TF tree by running this script. In addition, you can get the transformation between any 2 connected frames using TF command. For joint angles, you can directly print the topic in the terminal. You can also obtain these angles through ROS Python and C++ API. As for camera, you can add an image or a point cloud tool in RViz and subscribe the corresponding topic to see the result. As shown here, This is an image captured by Kinect. And this is a point cloud captured by RealSense. As you move the robot, the point cloud will change too. The raw data can also be accessed through ROS API. For controlling the robot and the gripper, you need to send messages to the two topics mentioned above. One simple way to move the robot is to move the blue ball in RVs. If you are not familiar with ROS, don't worry, we also provide Python interfaces. The source code and examples locate in the OCRTOC common directory. Similar to ROS topics, four major interfaces are provided, and we believe that these interfaces are sufficient to accomplish the task. Here are some examples on how to use Python interfaces. Backend and MoveIt should also be started first. Then we move to the OCRTOC common directory and run four examples. The first example is about the camera interface. In the example, you can know how to obtain color image and depth image in both ROS format and NumPy format. You can also obtain point cloud and camera information. The second example is the transformation interface. You can obtain the transformation between two frames in ROS and NumPy format. Third, we provide a gripper interface. You can set the opening width of the gripper through this interface. Finally, by using the manipulate interface, you can both move the robot given joint space target and Cartesian space target. After developing the program, you need to submit your solution. First, you should save your Docker image and then upload it to any available platform so that we can download the Docker image and do evaluation. As the source code is mounted into the Docker container, if you directly commit the Docker image, the file will be lost. Instead, you should unmount the directory first and then copy the source code into the Docker container. After that, you can commit your Docker image and upload it to any platform such as Docker Hub. After that, you can submit your result by sending us an email to info@ocrtoc.org. You should include a YAML file attachment. The template is shown here, which is also available on GitHub. The first part is some basic information about the team. The second part is about the track and branch of the competition. And the third part is about the Docker image. If the permission of your Docker image is private, you have to provide us with the username and password. Then, when we receive your solution, there are 6 steps for us to do to evaluate your solution. First, we pull the Docker image from the given link. Then we bring up the backend. If you choose to take part in the simulation branch, we will bring up the simulator. And if you take part in the real robot branch, we will bring up the real robot. Then we launch solution.launch and trigger.launch one by one. Finally, we will retrieve the 60 poses of each object after executing your program and calculate the score. As mentioned above, 2 steps are needed to calculate the score. The first step is to save the final object 60 poses to a file. In simulation branch, we read the poses directly from the simulator. In real robot branch, we will annotate the poses. The second step is to calculate the score according to the saved poses and target poses. In simulation branch, users can obtain the scores by launching trigger and evaluation.launch. The first 2 steps are the same with running baseline solution, that's to bring up the simulator and launch solution server. In the third terminal, you should launch trigger and evaluation.launch instead of trigger.launch. These scores will be calculated automatically when the trigger program terminates. The object poses is saved to a YAML file and the score is saved to a text file and also printed in the terminal.